Inside a modern hydroelectric facility, infrastructure operates on a massive scale. Massive volumes of water drive heavy turbines, demanding absolute reliability from every interconnected component. The critical link in this system is the hydro generator shaft. It connects the water turbine directly to the generator, operating constantly under a rotational torque of 35,000 Newton meters. This specific shaft fractured during operation, separating into two distinct pieces, a hollow midshaft section and a tapered transitional section. Examining the fractured edge reveals heavy oxidation lining the surface, indicating the metal tore completely through the cross-section. A mechanical failure at this scale causes immediate downtime and significant grid instability. Preventing a recurrence requires mapping the exact root cause of the fracture. This engineering drawing shows the baseline geometry of the failed shaft, focusing on the location where the hollow segment transitions into the solid terminal section. Detail C specifies how these two thick sections were fused together using a 60-degree single V weld joint. To construct this joint, engineers utilized an internal backup ring. Welded directly inside the hollow shaft, it supports the molten weld pool during fabrication. Under normal cyclic loading conditions, a welded joint has predictable vulnerabilities. Mathematical models dictate that failures typically occur at geometric stress concentrators. Statistically, the highest risk regions are the weld toe and the heat affected zone, or HCA, where the metal's grain structure is altered by extreme heat. Under visual inspection, the fracture bypasses the high-risk heat affected zone entirely. The crack initiated and propagated through the unaffected base metal. The dimensions were correct and the wall was thick. Yet the shaft failed in the exact region where predictive models deemed it most secure. To understand why the base metal fractured, we begin with the standard forensic procedure, verifying the material's chemical integrity. This chart compares the required specification against the laboratory results. The base metal contains 0.42% carbon, falling within the parameters for an ASTM Class M forging. This metallographic image shows the base metal's grain structure. It exhibits tempered bainite, which is the microstructure mandated by the processing standards for this alloy. We also have to confirm that the welding process did not inadvertently create a brittle or compromised zone, which requires a cross-weld hardness trace. This graph plots Vickers hardness across the three primary zones. As expected, the untempered bainite inside the heat-affected zone registers as the hardest region. Conversely, the unaffected base metal registers at 291 on the Vickers scale, placing it within safe tolerances. The chemistry is exact, the microstructure is correct, and the hardness profile is within specification. Material defect is eliminated as the cause. With the material cleared, we must look closely at the physical interface where the metal tore. This macro cross-section reveals the internal state of the weld root. You can identify the columnar structure of the weld metal on the left, the heat-affected zone in the middle, and the base metal on the right. Looking at this high-magnification image, the trajectory of the failure becomes clear. The main fatigue crack originates directly inside the softer, unaffected base metal. It travels straight through the base material, ignoring the heat-affected zone. This trajectory defies standard rules of geometric stress concentration. With the material verified as sound, a localized force is artificially elevating the stress state within the base metal, a characteristic signature of residual thermal stress. Welding residual stresses are locked-in forces generated by the localized thermal expansion and rapid cooling of metal during fabrication. During assembly, a continuous, multi-pass circular weld was carefully applied to fuse the heavy structural shaft components permanently together. The combination of a thick wall profile and that rigid internal backing ring creates extreme geometric restraint. The metal cannot freely expand or contract. Applying a continuous single-segment weld around the circumference traps intense thermal energy. The heat cannot dissipate uniformly, which builds internal shrinkage forces as the molten pool solidifies. To map these hidden forces, investigators utilized finite element modeling to reconstruct the precise thermal history of the weld. Literature assumes residual stresses distribute uniformly around a pipe. The finite element model proves this flawed. The thermal history generated a sharp, non-symmetric peak where welding started and stopped, revealing locked-in tensile stress exceeding 630 megapascals. This peak consumes 74% of yield strength. This tensile load sits permanently inside the metal structure, existing before the shaft ever experiences a single newton of operational torque. This non-symmetric residual stress peak provides the mechanical explanation for the failure of the base metal. To calculate the true strain on a component, engineers use the principle of superposition, adding static residual stresses and cyclic operational loads together. This graph plots the baseline stress. The static tensile load of 630 megapascals sits inside the base metal at the point where the weld was terminated. Once the massive hydro generator is activated, it introduces a continuous cyclic operational torque at 225 revolutions per minute. When this cyclic operational load is superimposed on top of the static residual stress, the total stress level rises. This combined load pushes the local stress state beyond the material's structural fatigue limit. While the hardened structure of the heat-affected zone could resist this peak, the softer base metal could not. It was pushed into a destructive low-cycle fatigue regime. The non-symmetric residual stress altered the mean stress ratio inside the joint, creating the conditions for crack initiation in the compliant base material. This forensic analysis carries implications for mechanical design across the power generation sector. Relying on uniform residual stress assumptions for thick-walled, single-pass joints leaves massive infrastructure vulnerable to extreme thermal peaks. One primary mitigation strategy is segmenting the weld sequence. Breaking the application into separate alternating bursts diffuses thermal buildup and limits localized trinket forces. The second mandate is rigorous post-weld heat treatment. To be effective, this treatment requires controlled heating and cooling ramp rates. This relaxes localized tensile peaks without compromising the required baonite microstructure. Accurate modeling of non-symmetric thermal stresses is the only reliable way to guarantee the real-world lifespan of critical power generation infrastructure.